Hi, Rowan. My name is Michael Rowan. I'm a NASAP for Simulations postdoc at NERSC. Today I'm going to tell you about using CUDA profiling tools interface for profiling asynchronous GPU activity. So this is work done primarily with Kevin Gott and Jack DeSlip. Okay, so in massively parallel codes, it's important to make sure that work is evenly distributed over the processes of the code or the ranks. And one such massively parallel code is the particle and cell code warpx. It's one of the exascale projects. And this is the team I've been working with to try and utilize an on-the-fly measurement technique of kernel execution time to have correct load balancing in the code. So there are several profiling tools available already, like NVProf or Nsight to profile NVIDIA applications. But these are tools that will generate reports and allow you to access kernel execution time after the fact. So for load balancing, if you want to load balance in a GPU accelerated code, you have to have some way to access kernel execution times on the fly. And so this is what I'll be telling you about today. So let's start with a simple example. What happens if we try and measure GPU kernel execution time in sort of a naive way, in the same way that we would measure the code time in a CPU. And so we're just going to suppose we start a timer, we launch a kernel, and then we stop a timer. And so you can just think for a second, what do you think we're actually timing here? And for people who are familiar with GPUs, you know that all we're measuring here is the launch latency. So we do a clock. This is what I'm showing in the diagram. We record our stop time, launch a kernel, and then we record the stop time. And all we've measured here is how long it took to launch the kernel. This is, of course, not at all correlated with how long it takes to execute the kernel on the GPU. And so this is sort of highlights a feature that complicates measuring kernels on GPUs, the execution time of kernels on GPUs. Okay, so the traditional approach fails. And the reason it fails is because CPU and GPU are, in general, they're asynchronous. So a kernel, it's a non-blocking, kernel launch is a non-blocking function. And so the CPU can launch the kernel, and then it'll go through and continue its work, and then the GPU will do its work. So we need some other way to measure kernel execution time than just trying to wrap like a timer around the kernel. So these are three alternative solutions to measuring the execution time of the kernel. The first is to count clock cycles on the GPU, and this is possible with the clock64, which is the clock64 function, which is you can count the cycles on the GPU using this. So the disadvantage with this strategy is that then you have to transfer that information off the device. And doing all this can be sort of invasive to codes. If you want to instrument the code to measure the clock cycles and then transfer off the device. So this was the approach that I tried first, but it turned out to not be too simple. So I'm going to cross this off the list. Another possibility is to use CUDA events. And CUDA events provides some timing feature for kernels that is syntactically very similar to just using like a CPU clock. But you generate these event objects, and then you can inject these onto streams for the GPU. And you can record timestamps for the events. This all sounds very good, and probably if you just want to measure, get a rough estimate of kernel execution time, this is a good strategy. But there are certain cases where it can give ambiguous results. And so this was also not the approach we ended up adopting. So the last tool that could enable real-time measurement of kernel execution time is CUDA profiling tools interface, which consists of several APIs. And this is the approach that we ended up adopting. So CUDA, or CUPTI, is actually the backend that enables NVProf and Nsight to do their profiling. But you can just use the calls from that library to get real-time access to the kernel times. And so I'll just provide a few more details about the cupd-based strategy that we used. So the first step with cupd is to initialize a trace. So this consists of a few steps. You just enable collection of certain containers or certain activity records that you want to collect. So there are several different types of activity records. There are kernel activity records and overhead activity records and lots of other things. But for our timer, we're just enabling the collection of kernel activity records. So you enable collection of the activity records, and then you need to register callback functions, which are going to handle request of buffers in which to store the activity records, and then they'll handle return of activity records back to the device from the host. And this is all dealt with by cupd, so you can just write your callback functions, and then those will be activated by activity on the GPU. So essentially, you do all this at initialization, and then you start CUDA, and then you can have the information containing the timing for the kernels just returned back to the host. Okay, so these are just schematic illustrations of the trace initialization, and then the callback functions, which handle delivery of the buffers containing activity records, and then which handle handle request of buffers in which to store activity records, and then to handle return of those buffers to the host. And so there are two callback functions. There's buffer request, buffer completion. Okay, so this to test our implementation of this cupd-based callback timer, we tested a very simple function, just a sleep function, which essentially it just instructs the device to sleep for a different number of cycles. So in this test, we're just requesting that on different streams, the device will sleep for multiples of 65 milliseconds. And this is what you see in this plot in the upper right. We have 4 streams, and we're requesting different sleep times. Ideally, the requested sleep time is shown in red. And then what we measure with cupd is this shown by the blue bar. So there is a little bit of overhead with cupd. This is, of course, a very simple example, but I'll show you in a moment for a more realistic use case what the overhead might look like. But the agreement between these bars indicates that cupd, of course, it gives accurate results. You're capturing the sleep time on all the different streams. And this bottom bar, this is sort of just a reproduction of what you would see in NVIDIA's visual profiler doing the same thing. So if you tilt this plot 90 degrees counterclockwise, it should give essentially this plot in the upper right. So that was for a very simple example. We were just requesting that the device sleeps on different streams. And so now I'll show how we implemented this in WarpX and try to use this for load balancing. And just to say a few more words about WarpX, this is advanced electromagnetic particle and cell code. And it's used to simulate laser plasma interactions. And I think later or tomorrow you'll probably hear more about some possible astrophysics, plasma physics applications as well. But it's built on the mesh refinement library AMRX. And so we implemented the timer in AMRX, and then this is how it's used in WarpX. Okay, so here is a picture illustrating the very simple test case that we set up in WarpX to test the cupd timers and then to test load balancing based on the cupd timer. So this is showing the initial setup. This red blob shows electrons and ions, so just particles in the code. The yellow grid is illustrating just the computational mesh. So this is something like, well, you can see this is by design a very load imbalanced problem. So all these central ranks are going to be doing all of the work, and then all to the left and right of this red blob, the ranks aren't doing anything because there are no particles there. So this is sort of another illustration of that initial setup, but it's just showing the cost per rank. And the cost here, since this is run on GPUs, the cost that we're computing here is something like a measurement of the time per rank in some normalized units. Okay, so initially you see ranks 4 through 7 are doing all of the work, and the others are not doing anything. And then, so now if we load balance, you can see the work is more evenly distributed. This is not a perfect load balance. Right now, the load balancing isn't taking into account like communications and other features apart from kernel execution time. So there's still work to be done, but you can see obviously that there's a large improvement in the way work is distributed over the ranks here. And this translates into large performance improvement, as you can see in this plot. So this is showing the wall time versus step in the simulation for one case which has load balancing, and that's the blue case, and then the dash red line shows the case without load balancing. So yeah, this demonstrates the importance of load balancing, and moreover, load balancing correctly. Like if you had tried to load balance based on what you were measuring with CPU times, it would just be not accurate. Okay, so second, another result here is to show the overhead that's actually incurred by using cupd and warpx, or the cupd timers and warpx. And as I said before, the overhead looked small in that bar plot where I was comparing the ideal sleep times versus what we measured with cupd. And now this is a more accurate case where you're launching like lots of kernels, and for all of the kernels, activity records will be captured. It's just that for the timer, when we're timing certain kernels, we'll actually access the information in those activity records. But anyways, you see that the agreement between the cupd case and the no cupd case shows that there's not too much difference in the total wall time between the two runs. Okay, so I'd like to wrap up actually by just summarizing the main points, the main results we have so far. So we developed a strategy to measure kernel execution time in real time. We implemented this in AMRX. And so the upshot is that this provides the possibility to do correct load balancing in GPU-based applications. So it's implemented at AMRX, but you could write your cupd timer for some other application as well. But this should be available soon for all AMRX applications. And in the future, we'd like to use this for more physical problems, such as ion acceleration, which are expected to be very load imbalanced. And therefore, we expect that this timer should be useful in load balancing for those type of problems. All right, thank you. If anyone has any questions.
Yeah.
So load balancing is actually a very hard problem, and this tool make it like possible to actually tackle this problem. So it's really nice.
Thank you.
My question was on the problem you show. Is
This
it
one?
a dynamic load balancing? Like, does the particle moves, and so you have to change the load balance
Yes.
in time?
Yes.
Can you repeat the question?
The question is if this is dynamic load balancing. So are the particles, if the particles are moving around, are you going to have to reload balance at different steps? Or yeah. Yes.
So what is your algorithm to balance between the different GPUs when the particles are moving around?
Yeah, so I mean, there are two algorithms that are implemented right now. There's one that is space filling curve, and then the second one is a knapsack algorithm. So space filling curve is meant to include, at some level, it's meant to account for communications. You want to minimize communications by making sure that there's one curve that fills the whole box. And presumably, well, it's something like it's accounting for communications when reconstructing how the mapping should be redistributed.
And the time you show take into account all this computation?
This was for the knapsack algorithm. Okay. So no.
So you mentioned that the CUDA events, like they're like ambiguous in result.
Yeah.
Is that a large overhead or like unreliable time?
So yeah, it's unreliable times. It's like you. Oh yeah, sorry. The question is, I mentioned that CUDA events can give ambiguous results, and I think the question was just how is it ambiguous? So I can give you a very specific example. If you suppose you have a kernel that's large enough to fill all of device memory, and you inject one kernel on stream 1, and then you inject that same kernel on stream 1. So two kernels injected on stream 1, and then queue that same kernel to stream 2. So the first kernel on stream 1 is going to execute in order. That'll fill the device. And then after that, due to the asynchronicity over the streams, the second two kernels, the device scheduler has a choice whether it could do either one of these, right? So if you do a CUDA events on stream 1, you might measure like 3 times the kernel time, or you can measure 2 times the kernel time, and that'll just change at runtime without any way to really predict that well. So yeah, just to avoid all of that, we use cupd. So
Thanks.
thank you.
More questions? So you've tested it with WarpX. Has anybody started to use it with any of the other AMRX code?
Not yet. I hope they will. So the pull request is sitting in the queue right now, but it'll be finished up soon, and then this should be available as any of the other timer macros they have right now.
Okay, the pull request meaning you're accustomed to pulled into the
Yeah. Yes.
Okay. I guess we have another 10-minute break. Oh, go ahead.
I mean, is there anything stopping this from being just a general GPU load balancer? I know you've applied it to the AMRX.
Oh yeah.
Is there anything specific to that works well for this balancer?
So
Repeat that question.
yeah, I think could the load balancer be applied to other problems outside of AMRX? Yeah, it could. I mean, the load balancer is sort of written into AMRX right now. But I mean, the algorithms you could use for other problems. And certainly the GPU timing, this is just a general strategy. And for our purposes, we wanted to try it with WarpX, so the natural place to put it is in AMRX. But you could just do the same thing in any CUDA application. You just initialize your trace, write your callback functions, and decide how you want to compute the execution time from the collected kernel activity records. So that part's definitely a general technique.